Welcome. So we are discussing plane frame structures. So in the last class we have solved one example. This example is essentially a two-member plane frame. So in this frame there is a horizontal load of 5 kilopound, and the one end is fixed and another end is roller supported. So we solve this frame by matrix method, or specifically the stiffness method, and this is our degrees of freedom. So we have started with node 1, 2 and 3. So there are 2 elements, essentially 3 nodes, and total 9 degrees of freedom. Among these 9 degrees of freedom we have 4 of which kinematic degrees of freedom are known, which is 2, 7, 8 and 9, and then the corresponding the load vectors which is known to us is 1, 3, 4, 5, 6. So with this we solved this problem and we found out the solution. The solution is this we have solved in the last class. So this is the D unknown, that means the partitioning of, after partitioning of the matrix we obtain this solution, and then once we obtain D unknown, so we obtain Q unknown by the second equation of the matrix equilibrium equation. Now here suppose if it is asked that you please find out the loads or the internal loading of the members, then essentially you have to find out what the loads acting at the node 1, node 2 and then node 3. So in the node 3 for instance, we know what is that all loads are acting in the node 3, because this is this will coincide with the internal loading. So this is Q7, Q8 and Q9, and then node 2 also we know what are the internal loadings. But if suppose if I want to know what is the internal loading at node 2, we do not know the internal degrees of freedom corresponding to 4, 5, 6. So in that case what should be the how should I find out? So to do that let us take the element 1 simply. So this element if I take now, we know from our previous calculation that this element is of length 20 feet. So this is 20 feet already we have discussed, or it is given this distance, and then what are the equilibrium for this element that we will explore to find out the internal loading in the node 2. Now lambda x and lambda y also we know, which finally results the identity matrix T. The transformation matrix is the identity matrix, and finally if you remember the formula for stiffness transformation, so this becomes Ke is Ke hat, Ke prime. So this, that means the local and global stiffness matrix are same because the element is entirely aligned with global xy axis or the structural xy axis. So with this we know what is the stiffness matrix, and the stiffness matrix is of this form that we know it. Now our objective is to find out what is the internal loading in this member. So to do that, before we start into that, let us see what are the equations we need to follow. if you remember that there is a transformation which is if you know the global displacement vector capital D, and then if you want to get the local displacement vector or deformation vector, then this is the transformation matrix T. So, this we know from our previous discussion, or even in the, from the first class itself we know this. Now, another important formula that we will use here is that the local equilibrium equation. For a member with small d is my deformation and q is my internal loading, and Ke prime is my local stiffness matrix, then the equilibrium equation reads like this. So, this form we will use it. So, now for this case the Ke prime d equals to q, where q is my internal loading. So, this I wanted to find out. Now, this d is again related to capital D in this way, because we do not know small d. We have found out only capital D. So, with this help of capital D and capital T, we can, or the transformation matrix, we can find out small d. Now, if we just substitute in this equation this, and then this leads to this formula, which is the q for the element small q, or the internal loading of the element 1, which comes from the equilibrium of the element 1. So, as you know that the all elements should be in the all members of the structure should be in the equilibrium. So, by this logic, this equation can be evaluated for finding out the internal loading of a particular member. So, in this case the element 1 T is my identity matrix. So, this becomes my equation for member 1. Now, naturally this will give me the K prime, K1 prime is this, and then identity matrix, and then this member contains 1, 2, 3, 4, 5, 6. So, D1, D2, D3, D4, D5, D6, and then corresponding Q1, Q2, Q3, Q4, Q5, Q6. So, this is my overall displacement and internal loading. Now, since we know D1, D2, D3, D4, D5, we can find out simply Q1, Q2, Q3, Q4, Q5. So, just by substituting this D1 to D6, that we have found out in the previous class, if we substitute it here, we get Q1, Q2, Q3 and Q4 and Q6. So, let us see how this Q1, Q2, Q3, Q4, Q5 and Q6. So, it turns out this. So, now if we draw the free body diagram, so if this member is having a shear force which is corresponding to Q1, Q2, which is downwards minus 1.87 kilopound, and similarly Q3 and Q4, that is the moment here is 0, and then the Q4 is the axial force in this side is 0, because there is no axial force in this member. So, here if you look carefully that this support, the node 1 was a roller support, it was a roller support. Now, this roller support means, that means moment has to be 0. So, this coincides with the our finding. Now, again at node 2 there is no support condition was there. So, but there is no axial force at all. So, in that member, to balance that, so there is no axial force. Now, there is a corresponding upward shear force 1.87, which is Q5, and then there is a clockwise moment, that is negative moment is 450 kilopound inch. So, this gives me the equilibrium of member 1. Now, if you want to draw a bending moment diagram, then you can just directly bending moment and shear force diagram, you can directly draw this bending moment and shear force diagram from this equilibrium free body diagram. So, now similarly we can find out for member 2, which if you find it out for Q say Q4, Q5, Q6 and Q7, Q8, Q9, then this looks this. So, here it is interesting to see that this 1.87 kilopound is acting this side. So, downwards here it is upwards, so which becomes 0, and then there is a anti-clockwise moment or the positive moment at this end for member 2. So, this is for the member 2. Now, this also balance. So, there is no moment acting at this joint finally, and then there is a external load 5 kilopound is acting horizontally along x axis, which is again balanced by the fixed end at this fixed end, because if you remember this end was a fixed end. So, this was balanced by 5 kilopound, and similarly this 1.87 is again balanced here, and then there is a counterclockwise moment of 750 kilopound inch. Now, these three reactions are very much matched with our internal reactions that we have or the reactive forces which we have computed in the from the previous calculation. But here at this joint 2, if you cut from the if you draw from the member 1 side and if you draw from the member 2 side, this is the free body diagram, or this is the internal forces that acting on this joint 2. So, this also with this knowledge you can also draw the bending moment and shear force diagram. So, this finally completes the problem 1. So, this is a part of the problem which were left in the previous lecture. So, this for each problem you can, once you solve the global degrees of freedom, or especially the kinematic degrees of freedom, that is D unknown, once you solve that, so you can go to the elemental level and find out the internal forces in the each member or the element. And then finally, once you found out the internal loading, then you can draw the bending moment and shear force diagram. So, this is the final answer to the problem. Now, let us do another problem, which is an inclined member. Essentially, this member is inclined along with an theta with x axis. So, this theta can be found out. So, essentially what we need is theta x and theta y with the member that is inclined with the x axis. So, this is my global y axis. So, this member, both the ends of this member are fixed. So, as we know, since both the ends are fixed, so the all kinematic degrees of freedom at these two ends are known to us, and there is a UDL acting on the horizontal member, that is 3 kilopound per feet, and these are the problem that I, A and E. So, these with this we want to solve this problem. Now, to solve this problem, the first step is to discretize again and find out what are the known degrees of freedom and unknown degrees of freedom, kinematic as well as the reactive forces. So, now here naturally the first impression is to discretize in this form, because this is node 1, node 2, node 3, and there is a node 1 corresponding to 1, 2, 3 degrees of freedom, node 2, 4, 5, 6, node 3, 7, 8, 9. So, among these 9 degrees of freedom, 6 kinematic degrees of freedom are known to us, because 1, 2, 3 we all know there is no rotations, no horizontal and vertical displacement. So, 1, 2, 3 is known, and similarly 7, 8, 9 is also known. But if you now see, if we discretize in this way, there is what we have seen it in the earlier example, that we need to shift the rows from to get the partitioning of the matrix, or to get the, or to separate it out, D known and D unknown, because you see your final global stiffness matrix Kg will be of this form. Now, in this Kg there will be a K11, K12, K21 and K22. Now, you see here this will come from 1, 2, 3 to 9, up to 9, and similarly 1, 2, 3 to 9. Now, to partition that matrix, essentially you have 4, 5, 6 is my unknown. So, 1, 2, 3 is known. So, this part will be known, and there are some other part will also be known. So, middle part of the matrix has to be separated out from the rest of the part of the matrix. So, you need the row operations, or the column and the column operations to separate it out. Now, this can be avoided if you choose judiciously the degrees of freedom, but again this is just for hand calculation. So, in a coding where you leave these operations for the computer, you really don't do that. So, I will explain one problem with this, how you can judiciously choose the degrees of freedom, so that you don't need to do matrix partitioning again. But again, the cost will be, you have to add the matrices properly while assembling. So, instead of choosing this setup, if I now choose little in a different way, suppose I choose, so this is the thing if I choose in this form. Now, instead of just shift these 2 degrees of freedom, that is if I just shift these 2 degrees of freedom, that is, if 1, 2, 3 if I put here, and 4, 5, 6 if I put here, then you see the node 1 is actually node 1 contains the 4, 5, 6 degrees of freedom, and node 2 is essentially 1, 2, 3 degrees of freedom, and then node 3 remains same with the previous case. So, let us proceed with this thing, and let us see how it will be done. So, if we choose this way, then my 1, 2, 3 is my unknown. So, you can see one issue here, that the first 3 degrees of freedom in a global stiffness matrix will be unknown. So, most likely we do not have to partition the matrix here. So, or the we have to partition the matrix, but the row operation and column operations probably we need not to do. So, this we can explain once we assemble, we can see once we assemble. Now, the Q, the force vector. So, since there is a UDL, so there will be a fixed end moment. So, we know what is the fixed end moment formula for these things. So, that is omega L square by 12, which is very well known. So, and these are the moments. So, this moment finally comes 1200 kilopound inch, and there is a shear force corresponding to 30 kilopound, because 30 and this is 3 into 20, so total 60, so 60 downwards, so divided at the two nodes 30 kilopound and 30 kilopound. So here these at these degrees of at this node there is only applied force, and these applied forces are 0, minus 30 and minus 1200. So these are my 1, 2, 3 is my non-zero means, or the active force vector. So now here 4, 5, 6 and 7, 8, 9 are my known kinematic degrees of freedom, and so my unknown kinematic degrees of freedom or unknown displacement vectors are 1, 2, 3, and corresponding the force vector is 0, minus 30 and minus 1200. This probably it has been explained to you in the beam also. So let us proceed now to find out the stiffness matrix. So the main objective here to highlight the matrix assembling or the assembling of the global stiffness matrix. So now similar to the previous problem, we just find out some quantities like AE by L, 12 EI by L cube, 6 EI by L square, 4 EI by L, 2 EI by L, and like that. So these quantities are evaluated with the data given, that is Young's modulus, I, moment of inertia, and area. With this we can find out these quantities. Now this member is essentially, if you see the coordinate of these members, if you notice the coordinate of this member. So this is the 20, 15 is the coordinate for this node 2, and this is naturally 0, 0. So you can calculate lambda x, lambda y, which is which relates to T matrix or the transformation matrix. So the procedure is pretty similar with the previous case, where essentially K E we write with T transpose K E prime T. So with this we can get the final stiffness matrix. Now in this stiffness matrix, the first 3 columns and first 3 rows are essentially corresponding to 4, 5, 6 degrees of freedom, and last 3 columns and last 3 rows are corresponding to 1, 2, 3 degrees of freedom. So this is the only change, and if you look carefully, that after transformation the matrix is not essentially the usual frame stiffness matrix with these quantities, these things are 0 and all those things, because transformation happened. But the property of the matrix remains same, it becomes symmetric, and this will be 696 I think. So the property of the matrix remains same, and but the it is not the same form as we have seen for the frame stiffness matrix, because of the non-zero transformation or non-identity transformation. So now similar to this case, we can find out the stiffness matrix for the element 2. Now in the element 2, again the coordinates, with the help of coordinates you can find out lambda x and lambda y, and since the length will be changed, because that was an inclined length we considered there. So here these quantities will also change, even though E, I and A remain same with the member 1. Now but length of member 1 and length of member 2 will be different, so that's why these quantities are different. Now similar to the previous case, we can find out the elemental stiffness matrix in the global degrees of global coordinate system. Now this global coordinate system, this T here is essentially a identity matrix. So it remains the same form with the local stiffness matrix or the K E prime. So here the first three columns and first three rows corresponding to 1, 2, 3 degrees of freedom, and last three columns and last three rows are corresponding to 7, 8, 9 degrees of freedom. So, this actually gives you the final stiffness matrix in the for two elements. Now, the next objective is to assemble this stiffness matrix. Now, you see this stiffness matrix I have written in a same page so that you understand this. This is my stiffness matrix. Now, the main objective is how to assemble this, or what is the assembling procedure for this, so that we get the global stiffness matrix. That we will discuss in the next class. So, I stop here today. So, in the next class essentially we will assemble and solve this problem. Thank you.